In this video, we will look at how to analyze an RC circuit using Kirchhoff's loop rule. The example we will look at is one of the simplest versions of an RC circuit. So the results that we derive might not apply to other variations, but the tools that we use, the methods that we use, can be used in a variety of problems. In this circuit, we have a battery connected to a switch, connected to a resistor, connected to a capacitor. We'll say the battery has EMF E, the capacitor has capacitance C, resistor has resistance R. We'll call the switch S. Initially, the switch is open and the capacitor is uncharged, so that we'll say that at t equals 0, the capacitor is uncharged, so we will say Q is equal to 0. At the moment t equals 0, we close the switch, and when we close the switch, a current starts to flow, which we will call I. As it's flowing from the positive end of the battery, this becomes the positive plate of the capacitor, this becomes the negative plate of the capacitor. Now that we have a complete loop, we will use Kirchhoff's loop rule to analyze the circuit. Starting at this point, we will go around the circuit in a loop like this. So first we cross the battery going from the negative to the positive. So we gain some potential. Then going with the current, we cross the resistor. So we lose potential, minus IR. And then we cross the capacitor going from positive to negative. Since we're going from positive to negative, we will lose potential. How much? Well, remember that for a capacitor, Q is equal to C delta V. And so delta V is equal to Q over C. So we are losing an amount of potential equaling Q over C. Once we cross the capacitor, we're back to our starting point. So the sum of all these changes must be equal to 0. There are two time-dependent quantities in this equation, the current I and the charge Q, but they are actually related. The charge Q on the capacitor is only there because the current brought it in. So in other words, the current is related to the rate of change of the charge. In this case, we have the current going into the positive plate, increasing the charge in the capacitor. And so we have I is equal to dq over dt. Plugging this in, we now have E minus R dq over dt minus Q over C equals 0. And we can rearrange this to solve for dq over dt. And we get E minus Q over C, the whole divided by R, is equal to dq over dt. And we can simplify that a little bit, getting EC minus Q divided by RC. Notice that this equation relates Q, which is a function of time, with the derivative of Q, dq over dt. This is an example of what we call a differential equation. So this is a differential equation for Q. Now that we know how to do integrals, we can actually solve it. To do so, we are going to bring all the Q-dependent terms on one side and move the other variables to the other side. So starting from dq over dt equals EC minus Q over RC, we move things around and get dq over EC minus Q is equal to dt over RC. To make life simpler, I don't really want this minus sign on the Q, so I'm going to pull out a minus sign and move it to the other side. Or you could say multiply both sides by a minus sign. And so I get dq over Q minus EC is equal to minus dt over RC. So you can see that I have all the Q dependent terms on one side and everything else on the other side. This is called the separation of variables. And I'm now ready to integrate. On the right-hand side, you can see that my variable of integration is time, because you can see that dt. And well, the time is starting at time 0 and going up to some time t. On the left-hand side, we know that at t equals 0, the charge is 0. So my q, which is the variable of integration, which you can see from the dq. So q is going to start at 0, and it's going to end at q of t. So at time t, the charge will be some q of t. On the left-hand side, since E and C are constants, we can find that this is a natural log. So we have natural log of q minus EC, the whole evaluated at the limits, q of t and 0. On the right-hand side, again, R and C are constants. So we end up with minus t over RC, evaluated at t and 0. So on the left-hand side, we have natural log q of t minus EC minus natural log minus EC. And on the right-hand side, we have minus t over RC minus 0. We recall that log of A minus log of B is the same as log of A over B. So we have natural log q of t minus EC divided by minus EC. And on the right-hand side, we just have minus t over RC. We would like to solve for q as a function of time. So to get rid of the natural log, we take the exponential of both sides. We have q of t minus EC divided by minus EC is equal to e raised to minus t over RC. Remember that the e here is not the electron charge. It is the base of the natural logarithm. So in other words, we're using e is equal to 2.71828, etc., etc. Moving things over and solving for q of t, we end up with EC times 1 minus e to the minus t over RC. So this gives us the charge q as a function of time. Let us examine the properties of this solution. One thing we will see as we examine other examples of RC circuits is that the more general form of this equation is going to be q of t is equal to some q final times 1 minus e to the minus t over tau. Now in this particular case, we can see that q final is equal to EC and that tau is equal to RC. But this form with QF and tau is more general. So what can we see from this solution? We know that the exponential, the exponent in the exponential has to be unitless, and so tau must have the same units as time. So it's a time constant. So tau is the time constant of the circuit. And that tells us, in fact, that RC has units of time. So that tells us that ohms times farads is equal to seconds. If we plot what Q looks like as a function of time, what we see is that at t equals 0, e to the 0 is 1, so you get 1 minus 1 is 0. So it starts out at 0, which is good because that's what physically makes sense. started out as an uncharged capacitor, and it then actually increases steeply before leveling off and asymptotically approaching the value of Q final. What this tells us is that when we first close the switch and the capacitor is uncharged, then a large current will start to flow through the capacitor, and the charge on the capacitor increases very rapidly. However, as more and more charge accumulates on the capacitor, it becomes harder to add further charge. This makes sense because think about what we're doing. When you have a capacitor with some charge on it, you have some positive charges on one side and some negative charges on the other. To increase its charge even further, you would need to bring in another positive here and extract a positive here, leaving another negative on this plate. But that becomes harder and harder to do. It becomes harder to bring in a new positive because it's repelled by the positives which are already there. It becomes harder to extract a positive because it is being attracted by the negatives which are there on this plate. And so as time passes, the charge does not change as rapidly anymore and eventually approaches an asymptotic value. Of course, it technically takes an infinite amount of time to reach that asymptotic value, but we will see that usually waiting 5 times tau is enough for you to reach 99% of the final value. Remembering that I is equal to dq over dt in this case, we can find the current as a function of time. And that turns out to be q final over tau times e to the minus t over tau. If we plot this graph, then as expected, we see that the current starts out at a large value, but then exponentially decays down to 0. Of course, the starting value here is equal to q final over tau. And we know that tau is equal to RC. And unit-wise, that all makes sense. So to simplify our analysis, we can say that for a charging capacitor, when the capacitor is uncharged, there is very little charge on the capacitor, and so there's very little voltage drop across the capacitor, and the current flows through it freely, so the capacitor behaves like a plain wire. On the other hand, when the capacitor is fully charged, so when a long time has passed and the capacitor is fully charged or nearly fully charged, then we know that it is hard for current to pass through the capacitor. And so the current has died down to 0, and the capacitor acts like a broken wire. It doesn't let any current through, but there is a potential difference across the plates. Remember that a capacitor is not the same as a resistor. For a resistor, if there is no current, there is no voltage drop. But for a capacitor, as long as there is charge, there is a voltage drop. And so a fully charged capacitor has a very large voltage drop across the plates. So this is the case of a charging capacitor. Let me just write that here. This was a charging capacitor. Next, we will look at the case where we start with a fully charged capacitor and discharge it instead. For our discharging capacitor circuit, all we need is a capacitor, a resistor, and a switch. Capacitance C, resistance R, switch S. Let us say that this is the positive end and this is the negative end of the capacitor. At time t equals 0, we will close the switch, and we know that at t equals 0, the charge on the capacitor is some initial Q naught. What happens when we close the switch? Now current will flow out of the capacitor, that is out of the positive plate of the capacitor, through the resistor and into the negative plate because the capacitor is discharging. So now our current is flowing out of the positive plate. The capacitor, in a sense, is acting like a battery. However, unlike a battery, who ideally the voltage will stay constant, here as the capacitor discharges, its voltage will start to drop. Furthermore, because here the charge on the capacitor plate is decreasing as the current flows, we will say that the current I is minus dq over dt. And this applies whenever you have current flowing out of the positive plate of the capacitor. Once again, we do the loop rule. We'll start over here and go around counterclockwise. So first we cross the capacitor, going from the negative to the positive. So we are gaining potential, and the amount that we gain is plus Q over C. Then we go across the resistor, and we are going with the current, so we lose potential, so minus IR. And then we are back to our starting point, so equals 0. Again, remember that I is equal to minus dq over dt because the current is coming out of the positive plate, so it is decreasing the charge. Using that here, we have q over c plus r dq over dt is equal to 0. And we can rearrange that to get dq over dt is equal to minus q over RC. Once again, we have a differential equation for Q. This is for a discharging capacitor. Again, we use separation of variables. So we have dq over Q is equal to minus dt over RC. Integrating both sides, on the right-hand side, we are going from time 0 to time t. On the left-hand side, we are starting with an initial charge Q0 and going to some final charge Q of t. On the left-hand side, this evaluates to log Q, evaluated at Q of t and Q0. And on the right-hand side, we have minus t over RC. Again, on the left-hand side, we have log of Q of t minus log of Q0 is equal to minus t over RC. Log A minus log B is the log of the ratio. So we have log of Q over Q naught is equal to minus T over RC. We take the exponential of both sides to get rid of the natural log. So we have Q of T divided by Q naught is equal to e to the minus T over RC, or Q of T is equal to Q naught times e to the minus T over RC. And the general form of this is Q naught times e to the minus T over tau. This is the equation for a discharging capacitor. Looking at the properties of this solution, if we plot the charge as a function of time, what we see is that it has an exponential decay. Starting value, of course, is Q naught. If we look at the current, well, remember that I is minus dq over dt because the current is coming out of the positive plate. And so this gives us Q naught over tau times e to the minus t over tau. And if we plot this current as a function of time, then what we see is that we start out with a large current, but then it exponentially decays. Here, the reasoning is that initially there is a large potential difference across the capacitor driving the current. However, as the capacitor discharges, it's a victim of its own success. And in its discharging, decreases the voltage across the capacitor and thus decreases the current that is driven through the resistor. So a discharging capacitor acts a bit like a battery, but it is a battery that dies. Right? That concludes this video.